Special guest today is Sarthak Duary from YMSC, and he will tell us about from the closed open strings to open strings, the tensionless root and Kalb Ramond background, and noncommutativity. So please, Sarthak.
So thanks for the invitation. And today I will talk about from close to open strings and the tensionless root in Kalb-Ramond background and non-commutativity. So this is a work that I did with Saurabh Maji, who is a postdoc at Harishchandra Research Institute in Allahabad, India. So these are the outline of my talk. So first I will introduce the basics of tensionless strings, and then I will go to the tensionless strings in presence of a uniform Kalb-Ramond field, and then I will discuss the transition from closed to open strings. So basically here I will show the closed tensile string, and when you take the tensionless limit, it will be tensionless emergent open string. And then I will discuss that in the presence of the uniform Kalb-Ramond background, what is the boundary state. And the second part of my talk, I will talk about the derivation of non-commutative parameter. First, I will talk about the tensile theory, and the sketch is the following. So here I will follow the symplectic approach, and the approach is that you can derive the non-commutative parameter from the boundary to form symplectic potential, and from the boundary symplectic potential you can compute the boundary symplectic form, and the boundary symplectic form, the kernel of it, from that you can extract the Poisson tensor. And in the second, so this is the sketch of the derivation of the non-commutative parameter. Then I will discuss the non-commutativity in tensionless strings. So first I will give first I will give a tensionless reduction from the tensile theory, and then I will give an intrinsic derivation of the non-commutative parameter purely from the tensionless string theory. First part, I will talk about the tensionless strings in the uniform Kalb-Ramond background, and I will show that how it modifies the boundary condition, and how it modifies the induced vacuum state. So which I call the generalized induced vacuum state, because without the B field, people already studied the induced vacuum for tensionless string theory. So here I will refer the generalized induced vacuum state, and so this state I will discuss, and that leads to the generalized gluing between modes. And this deformation is encoded in some gluing matrix, and this gluing matrix also involves the antisymmetric Kalb-Ramond field, and this interpolates between the standard Neumann boundary conditions and the background deformed person. And then I will present the result for the induced vacuum for the boundary state, and this will give some continuous evolution from the closed string vacuum to an open string configuration in the tensionless limit. And the second part, I will talk about the non-commutative parameter. So the non-commutative geometry has long been recognized as a fascinating feature of string theory, particularly the dynamics of open string moving in background fields. So this goes back to the work of Witten and Seiberg-Witten, and there are this Sheikh Jabberi and the other work that Braga Goldino. And so the idea that the coordinate of spacetime might fail to commute finds a natural realization, and it happens for some antisymmetric B field. And then the inverse of the two-form symplectic form gives you the Poisson brackets on the boundary coordinates, and the endpoints of the tensionless string do not commute. So this background field induces a natural non-commutative geometry on the space which the string probe, and the strength of the non-commutativity depends on the B field. So in this derivation, there is a usual approach which was given by Seiberg and Witten, and they compute it using the 2-point function in tensile theory. But for the tensionless case, this usual approach will no longer hold because the 2-point function here cannot is little bit different. So standard 2D CFT machinery is no longer available here. So I will follow a different approach. So this approach is the symplectic formalism, and that operates purely at the classical level of the action, and that identifies the boundary phase-space structure through the symplectic 2 form. So first you will compute the symplectic potential, and from that we will get the symplectic 2 form. And this approach is also can be applicable for tensionless string theory. And so I will follow this approach. So since the standard operator approach is no longer valid, so that is why I will follow this boundary symplectic form, and I will compute the non-commutative parameter using this approach. So these are basically the overview and the summary of some results, but I have not told you, introduce you any basic things about tensionless strings. So let me first briefly review a bit about tensionless strings, very basics. So from particles to strings, so we know that massless particles follow null geodesic, and these are the light-like, and their world lines are actually null. So they follow null geodesics in space-time, and the null string or tensionless strings are the extended analog of the massless point particle, and they just so basically the 1D extension, so 2D extension of this massless point particle are the tensionless string, and thus tensionless string is a natural generalization of the massless point particle, and the study also dates back to the work of Seil. And so now in usual string theory, we have a string tension, and string tension is just 1 by 2 pi alpha prime, and alpha prime is related to the string length. And when we can take a point particle limit of the string, and in the point particle limit, the string theory or superstring theory action will reduces to Einstein gravity or supergravity. So this is the alpha prime going to 0 limit, or t equals to 1 by 2 pi alpha prime going to infinity limit. And the tensionless limit is the opposite of that limit. So that means that alpha prime going to infinity, and strings become very long, and t equals to 0 limit. And so how one can construct intrinsically the tensionless string theory action. So now we can, so in the string theory, we have the Polyakov action, which is describes the motion of a string in a flat d-dimensional background, and here the metric, target space metric is eta mu nu, and these gamma ABs are the worldsheet metric. And so in the Hamiltonian approach, if you take the tensionless limit, so and you go from in the Hamiltonian approach, then you will find that the worldsheet metric will become degenerate. That means the determinant of gamma is 0. And so the idea here is that you replace the t square root of minus gamma and gamma AB with the VA VB, and VAs are the vector densities on the worldsheet. So this construction was given by the Isberg, Lindstrom, Schoenberg, and Theodoridis, and this is the ILST action. So this is actually an intrinsic action without any other meaning the parent action. So this is an intrinsic formulation, and this is this you can think of it as tensionless strings as a standalone theory. And here the worldsheet dynamics is encoded in the VA and VB. These are the vector densities on the worldsheet, and we will not refer to any worldsheet metric. And this perspective treats tensionless strings as fundamental objects in their own right. So basically, if you want to do any computation in tensionless string, you can start from this action and do anything. So this is an intrinsic action of the. Okay. Okay. Yes. Yes. Here. So here this, I think this null is basically just you can think of it is that the mass, the equivalent thing of the mass here is the tension, and mass going to zero is equivalent to tension going to zero. So and so
We know
yeah.
P as before as a spectrum,
Yeah.
which depends on alpha prime, which is the only scale you have, and then you want to take alpha prime to zero, infinity.
Yes.
And this means that all states became flat. Or if you wish, the geometry, the target space geometry becomes very, very quantum.
So this
that is flat becomes a very natural assumption.
Saying that so basically the fluctuation will deform the geometry, you are saying, because the quantumness. So yeah. So I think yeah, I understand this point. I think the general idea is that it can deform the geometry. I think there are some works also. Tensionless string can deform the background geometry, and background becomes Carrollian. But in whatever I will discuss, I will assume the flat metric. So there is a idea that
the other state asking where they go. Being 2 billion guy,
yes,
will be very light.
Yeah.
So you cannot say, don't look at it.
Yeah, I understand this thing, but has been states becoming the light states actually.
All right, also consistent. If I have to be very big, last year, it's not well, but that is the standard theory. Goes along with the Grossman thing. What I mean is you have this in the tensionless, you have this power of vessel excitation, which is
the whole tower. Yes.
tensionless is not way strings which are quote unquote hard. But the log string has a lot of noise, just all the vibration. And so all of these are masked.
Yes,
What is the three? Contact. Yeah. The second question is how this is related to the physical. That there's some connection or this. When I study this apart,
okay. I somehow this the working. So let me just say some basic facts actually. So the normal, so here also there is a worldsheet diffeomorphism invariance, and the tensionless string action also is invariant under worldsheet diffeomorphism, and just like the tensile string, and one particular like the conformal gauge here is the VA vector density is you fixed to V comma 0, where V is a constant. And this is the analog of the conformal gauge. And after in usual tensile string theory, after fixing to conformal gauge, there is a residual gauge symmetry. And for normal closed tensile theory, this is the two copies of the Virasoro. And so here the symmetry for usual tensile theory, the residual symmetry after gauge fixing is the Virasoro. And the generators of this Virasoro symmetry is the Virasoro generator, and that satisfies Virasoro algebra. And for open string, it is the single copy, and for closed string, it is the two copies of Virasoro. And for tensionless, the symmetry is the 3D BMS symmetry, Bondi-Meixner Sachs. And the generators of that symmetry satisfies the BMS3 algebra, and this is the 2D conformal Carroll algebra. And for open string, there are also recent people are working on it, and they call it the boundary conformal Carrollian algebra. The generators of this symmetry satisfies. Talk about tensionless limit as a worldsheet Carroll limit. So, tensionless limit, the string becoming long and floppy. So in terms of the worldsheet coordinate, we can also view that you can take the sigma going to infinity limit, and so equivalently you can view it as tau going to epsilon tau and sigma going to sigma, and you define also a new scaling parameter C prime, alpha prime going to C prime by epsilon, and you can take epsilon to 0 limit. And this is referred to as the ultra-relativistic limit on the worldsheet. So this is a limit in which speed of light on the worldsheet vanishes. So basically, in terms of the worldsheet velocities and the speed of light, we can say that sigma by tau is same as V by C, and when you take the sigma to sigma and tau to epsilon tau and take epsilon to 0, then sigma by tau will becoming infinite. So that means that this C going to 0. So that this limit is basically the ultra relativistic limit where the speed of light on the worldsheet actually vanishes. And so this is a picture that you can take the sigma going to sigma, tau going to epsilon tau, and epsilon going to 0. So this is the tensionless limit from the worldsheet, and this is as the ultra relativistic limit, and referred to as the worldsheet Carroll limit. So now I will talk about the generalized induced vacuum condition in the presence of uniform Kalb-Ramond field. So we consider here the tensionless string and tensionless string action and with a Kalb-Ramond field. And so I showed you the ILST action in terms of the vector densities on the worldsheet. And then the modification here is that epsilon AB B mu nu is the Kalb-Ramond field, and del A x mu del B x mu. And this B mu nu is an anti-symmetric, and this is B mu nu is minus B nu mu equals to constant. And then I fix a tau boundary, and which is Na equals to 1, 0. And the boundary condition for this is basically del tau x mu plus 1 by 2 pi B mu nu del sigma x nu equals to 0. So then the idea here is that you can expand your tension mode in terms of this tensionless oscillators B naught and A mu and B mu. So this is the mode expansion, and we also define C mu n and C tilde. So these that we define basically because this C and C tilde satisfies the harmonic oscillator algebra, and then we will write this boundary condition, and it gives basically the eta mu nu plus 1 minus in tau by 2 pi B mu nu times C plus eta mu nu minus this 1 plus in tau by 2 pi B mu nu times C tilde, acting on the state which we call as the generalized induced vacuum state. And then we can take that tensionless limit and tau going to epsilon tau and sending epsilon to 0. So in that limit, basically eta mu nu plus some constant time B mu nu times C plus eta mu nu minus some constant time B mu nu C tilde acting on the IB equals to 0. So you can also rewrite this in terms of C mu n plus R mu nu C tilde nu minus n acting on IB equals to 0. And R mu nu is the gluing matrix that also encodes the information of the B field. And now this is a generalized induced vacuum state. So basically by that I mean so the gluing condition now is changed. And now you can think of it, this equation, as you can take a B going to 0 limit, and that all agrees with the induced vacuum state in the usual tensionless string theory, and this is a generalization. So this we call as the generalized induced vacuum state. And now I will discuss, so now this gluing condition is the generalized induced vacuum state, and now you can solve it. So you can write the IB in terms of the exponential of this minus 1 by n C mu minus n R mu nu times C tilde acting on some 0 C. I will also discuss what is the physics behind it. But for this is just a solution, and solution of this induced vacuum state, and this prescription was also similar to the CFT that people also I think familiar with. Yes. 0. Yes. Yeah, you are saying the non-relativistic limit you are saying. So in that limit, actually the idea is that VA will be changed, and I think you can do it actually. Yeah, it will be changed, I think. I have not talked about this. Here, the idea is that if you take the B going to 0 limit, then you get the C mu n plus C tilde mu n acting on I0 equals to 0, and this corresponds to the Neumann boundary state. And this means that Neumann boundary states describes an open string whose endpoints are free to propagate. And now I will discuss the physics behind this. So you can have tensile modes. So alpha mu and alpha tilde are the tensile mode oscillators, and here C mu and C tilde are the tensionless modes. And these two oscillators are related through a Bogoliubov transformation. So this cos hyperbolic theta and sin hyperbolic theta are basically a linear combination of epsilon. So basically the here this will be just cos hyperbolic theta is square root of epsilon plus 1 by square root of minus epsilon, and sine hyperbolic theta is this thing. And so basically the tensile modes and tensionless modes are related by this relation, and then you can construct a tensionless vacuum and tensile vacuum. So this will be related by exponential of Ig, the generator of this transformation, and you will get exponential of tan hyperbolic theta by n, C minus n dot C tilde minus n. This means that the tensile string vacuum is related to the tensionless string vacuum. And now what we can do is that you can tune your epsilon from 0 to 1. So epsilon is a parameter. When epsilon is 0, then tan hyperbolic theta is minus 1, and epsilon going to 0 is the tensionless limit. And if you take epsilon going to 1, then this is the usual, you are not taking any tensionless limit, so you will get a closed string vacuum in the tensile is equal to the tensionless closed string vacuum. But when you take the epsilon going to 1 limit, in that limit, this state 0 alpha will basically becomes exponential of minus 1 by n. So tan hyperbolic theta becomes minus 1. And this is the same state that I introduced for defining the induced vacuum. So what this means that the closed string tensile string vacuum, when you take the tensionless limit, the vacuum itself, the state itself going to the induced vacuum state, which is the open string state. And so the idea here also can be interpreted in terms of the space filling D brane. So basically an open string can move in the space and free to move in all dimensions, and that can be that naturally comes from a closed string from a tensionless limit. So in terms of the picture, an open string Neumann boundary conditions along all space-time directions is equivalent to a space-filling D25 brane in the bosonic string theory. So you have a tensile closed string, and it can fill all of the space and becomes a space-filling D brane. So there are other equivalent picture also. So you have closed tensile string, and you are basically just string this thing, and it becomes a open emergent open string. So basically, the two vacuum, tensile and tensionless two vacuums are related by the Bogoliubov transformation, and generally this state is a squeeze state. But when you take the tensionless limit, the left hand side, that vacuum is the same as the induced vacuum state. So, and in the work that if you introduce B field, that induced vacuum will also become the generalized induced vacuum, and after taking the B going to 0 limit, this gives the induced vacuum state in the intentionalist theory. Explain it more. Basically, here there is no open string in the picture. Here both are closed. This is closed, this is closed. So this is closed tensile string, closed tensile string vacuum, and this is closed tensile string vacuum. And when you take the epsilon going to 0 limit, then tan hyperbolic theta becomes minus 1. And in that limit, you will get this state. And this state satisfies C mu n plus C tilde mu n acting on the vacuum is 0. And this can be thought of as the Neumann boundary state. In that sense, this is the picture. So this picture is this closed tensile string, and closed tensile string, when you're decreasing string tension, then basically this string will shrink actually, and basically you can draw this picture like you can shrink this to end, and if you shrink this to end, then it becomes open string. So this is a actually pictorial representation. Just picture is actually yeah, strictly. I think in the finite tension, this state is the squeeze state. No longer can be thought of as the induced vacuum state. So this is generally squeeze state at finite epsilon or finite theta. But when you take the epsilon 0, then this manifests. Yes, strictly. I think no. Yeah, any infinitesimal variation can deform the state. Uh, yes. Not use any dimensional restriction. The dimension is also fixed. I think induced vacuum will not change the dimensionality.
That's why induced vacuum actually doesn't have a critical diameter. It is not needed critical diameter.
Yeah, I think there are also some work I think for other vacuum.
But other vacuum,
So then,
for now there are three kind of vacuum flow. I mean three kind of theories, quantum theory. And for three quantum theories, the anomalies are different. And accordingly, critical dimension for other theories is 20. For this particular theory, it is intrinsically the critical dimension does.
void in there. So here, glue these two pieces together. Meaning, if you glue this, then it becoming this. This is just a picture. I don't. Uh, I think. The other part, the here I. Okay, you are saying the vacuum I only consider. your point really. Let me recall if this is an alpha mu minus n and alpha tilde acting on this vacuum and create the excitations of these oscillators. I the non-commutative parameters. So this first I will discuss the tensile string part, and I will give an independent derivation without and the symplectic derivation actually. So you can take the action, and here the dot and primes are the delta and del sigma derivatives, and the boundary condition is gij times x prime plus 2 pi alpha prime times bij x dot j equals to 0, and you can compute the canonical momentum also here. And now you can have a notion of pre-symplectic potential, and which is the mechanical analog is that pi delta qi. So you can think the theta sigma as some d sigma pi I delta xi, and you can take an exterior derivative of that pre-symplectic potential that gives you the bulk symplectic form. So which is omega sigma is the delta theta sigma, which is d sigma delta pi I wedge delta xi, and for an open string, the boundary condition constrain the x dot and x prime at the endpoint. So the independent degrees of freedom lives on the boundary phase space. So now I will define the boundary symplectic potential, which is restricting to this delta sigma. So theta delta sigma is thought of as restricting to this boundary condition, which is gij x prime j plus 2 pi alpha prime bij x dot j equals to 0, and its exterior derivative gives us the boundary symplectic form. And when b equals to 0, this defines the standard Poisson bracket for the field x mu and pi mu, which is x and pi Poisson bracket give you delta mu nu times delta sigma minus sigma prime, and pi mu and pi nu Poisson bracket gives you 0, and x nu Poisson bracket also give you 0. But in presence of B field, these relations will no longer valid. So now you can have the boundary condition that can be written as a matrix form g x prime plus 2 pi alpha prime b x dot equals to 0. And you can rewrite x prime in terms of x dot, and you can first write the momentum, so pi in terms of g x dot plus b x prime by varying this action, and you can then rewrite x prime in terms of x dot, and you can write pi fully in terms of x dot. So this gives the A matrix, which is written in terms of the G and B also. So this has 1 by 2 pi alpha prime G minus 2 pi alpha prime B G inverse G. And with this notation, you can compute the symplectic potential, which is that theta delta sigma. And this can be written as x dot transpose A delta x. Here, this is a matrix multiplication. And then you can take the exterior derivative in field space that give you the boundary symplectic form. So you can, a more convenient way to arrange this computation is you define this E and E transpose. So here G transpose is G and B transpose is minus B, and you can define E as G plus 2 pi alpha prime B and E transpose as G minus 2 pi alpha prime B. And you in this way you can rewrite A in terms of E and E transpose, and finally you can get the sigma of delta sigma in terms of that AIM matrix. AIM is defined as E G inverse E transpose. So here I will not present the full computation, and this involves a lot of details. But finally, you get the symplectic 2 form as some dxi with dxj kij, And here Kij is the kernel of the symplectic 2 form. And so the Poisson tensor is defined as the inverse of the kernel of the symplectic 2 form. And you get the theta tensile in terms of G plus 2 pi alpha prime B inverse B and G minus 2 pi alpha prime B inverse. So this is the theta tensile. And this is the formula that this Seiberg-Witten, but I derived it using a symplectic approach, and this is the non-commutative parameter. So in our paper, we derived it. I think the boundary is defined in terms of, I think this product is the Moyle star product, the boundary. Yes, 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 yes. So this is the derivation, and here when you take the tensionless limit, then t going to 0 or equivalently alpha going to infinity. So then, and here in this notation you have alpha prime going to infinity. So this term dominates. So then you can define f is 2 pi alpha prime b. So then you can write E as G plus F, and this term is dominating, so this is F, and E transpose is minus F. So you can rewrite you can do a tensionless reduction. So, and this 2 pi alpha prime square will cancel with the 2 pi alpha prime to the power minus 2, and indeed you get a B inverse in the tensionless limit. Now what I will do, I will present an intrinsic derivation without going to the tensile string theory. And so we start from the ILST action, null string action, in the gauge VA, which is V0, and V square is 1 by 2 pi C prime. And we write this in terms of ILST action. And here Bij's are taken to be constant, and the equation of motion give you the x double dot I equals to 0. This is a related. You just also need to scale your B field, B mu nu by B mu nu by alpha prime. Then you can take the B mu nu as some rescaled B. Yeah. Your point. So you were saying the Polyakov, and when I write the B, I use the same B, but it's not, because I think if you treat the same B, then it is not well defined actually, because there is alpha prime here. Yeah, I will think that, yeah, I need to, yeah. I take the tensionless reduction, then I don't need to scale anything. This gives you some independent. Yeah, this be, I think, yeah, can be different, I think, from this, I think, what you, this is, I think, one, yeah. So here, if you require this delta x equals to 0, then you get gx dot plus bx prime equals to 0, and this is the boundary condition. And you here can see that the canonical momentum density is also vanished. So that is why we require the some different approach, which is the first order structure. So we can take the action which is linear in x dot, and we take the canonical one form, the symplectic potential, by varying this Lagrangian, which is the del L by del x dot, which gives you Bij x prime, and we can write the boundary symplectic potential. And if we take the exterior derivative in field space, this gives you the Bij delta xi OH delta xj. So you get the 1 by 2 pi Bij, whose inverse is 2 pi B inverse. So thus the equal time Poisson bracket will read the, so xi sigma xj sigma prime or delta sigma is 2 pi B inverse delta sigma minus sigma prime, and upon quantization you will get the I times 2 pi B inverse ij delta sigma minus sigma prime. So this gives an intrinsic derivation of the non-commutative parameter, and I don't know why this thing is appearing. No, it is not my computer. I think it is not. Oh, maybe. Okay, I think it is in my slide actually. So we established a inclusion of a constant antisymmetric Kalb background modifies the induced vacuum, and that leads to a generalized gluing condition. And this deformation in a constant gluing matrix that smoothly interpolates between the standard Neumann condition and the background deformed version, and the resulting induced state forms the squeezed boundary state, and that is the idea of the closed string vacuum to an open string configuration. And then we also studied the symplectic origin of the non-commutative structure in the constant background, and starting from first principle, we showed that the tensile and both tensionless strings can be described within a unified framework. And we can take a tensionless reduction and get the non-commutative parameter, and also we also give a intrinsic derivation from the tensionless string theory also. And the future directions is actually we can generalize to superstrings, and you can also introduce some slowly varying background, inhomogeneous. And other thing also I think is interesting is that you can introduce some world volume gauge field into your theory, and that can change the non-commutative parameter also. So yes, so these are the things that I want to say.
Sure. There have been some questions already, but more questions and comments. I think just one precision.
Yes.
So literally, these slides you can go back, but
Okay.
you're somehow implicitly you have this Zyber-Quitton map argument,
Yes.
which states that you are having like non-commutative background,
Yes.
which you can replace by commutative, but put in fluxes.
Yes.
So this is what you say. This is along the lines what Hussein was asking, that you have this B field,
Yes.
but this is not the initial B field that I would be adding to the conventional worldsheet action.
Yes.
So can you go back to the slide? I just want to see the properties of this B.
Okay, so I have not written, but I'm just saying that your tensile theory has some B, and you so basically in the action Polyakov action there is a 2 pi alpha prime here. So in the tensile theory there is a B mu nu, right? So I'm just saying what we can do is that you can rescale your you can define a new B, which
Exactly.
is rescaled version of B divide, because otherwise this does not give you any limit, I think. But
that is a must, because the Zyber-Quitton map also
yes.
It's a transformation that would be transforming your B.
Yeah.
Forming the flux on this commutative way.
Yes, I'm saying, I think here there is no such other thing cannot required, because epsilon AB is antisymmetric, but for the usual the worldsheet metric is actually degenerate, so that is why you require VA VBs on the worldsheet. But here only thing is that you need to rescale your B only. Yes.
Compactifications.
Yes.
This is the rest is standard.
Okay. Yes.
Okay.
The action that you started with, the action of the
Oh.
tensionless string.
Okay. For the non-commutativity derivation, you was okay. This B, when you start from the tensile, this will be rescaled version of the original. Here you don't need to do anything. Here you need to do extra things here. VA, VB. This is the thing, I think.
I mean, the B field, we always say that the generalization of, say point particle action in electromagnetic field, B field is considered generalization of that. And now the thing is that when we take the tensionless limit, it's ultra high energy limit. Now, if we take the field finite, original field finite, and take ultra high energy limit on the particle, I mean, the effect of the field on the particle should not be visible there. Now we have to dial the strength of the field also infinitely large to make its effect visible. And that is how we think.
Yeah, I
about
think this is one. I think you also need to rescale your.
Physically,
Yes, I think.
Question about this tensionless string.
Okay.
New to this thing, so
Okay. I also
Is it,
don't know much about this, but I am also very new. But you can ask me.
okay. So how to quantize this action?
I have not studied. Yeah.
actually, if we use the standard time constant on the constraint of particular, there are so far actually there are three possible ways it was counted, and three possible ways led to three different results.
Because three different.
Actually, it is not that one. Bogoliubov function also has multiple ways to quantize it.
Right. But but at least they have a consistent. They have consistent spectrum.
Yes.
Right.
And actually, two of the three theories get
Yes, and in
directly
flip.
from limit of different Bogoliubov quantum quantities. I mean, the states we find out in the tensionless quantum, they can be found from different from direct limit from two different tensile the Bogoliubov string quantum. There is a another one. They did actually Bogoliubov action. They studied in a actually Virasova algebra. Usually, if you are on a accurate representation of Virasova algebra, and there is another representation of Virasova algebra there. That's called
For some other string theory like MB string theory.
that's one of the versions.
So because for tension string there is no this Carrollian structure, so they should be organized as representation of Carrollian algebra.
This theory belongs to the induced representation of the BMS algebra. And there is another version which is constructed on the highest representation of BMS algebra. Now, the induced representation of BMS algebra comes from the highest representation of Virasova algebra. And the fifth representation of the Virasova algebra we are talking about. If you take Carrollian, it will give us the highest representation of BMS algebra. That is how it works in the representation in that way, and the physical states also work accordingly.
So then, because this tension is so everything is messless for this. It's messless.
Actually, yes,
There's no tachyon, there's no.
Yes. In case of the oscillator harmonic, that is not actually we never found any tensile counterpart of that one. Here, actually, strangely, there is mass spectrum, and the mass spectrum somewhat similar to tensile. Actually, there is some tachyon like the oscillator vacuum with the strange one, and we still do not fully understand that one.
Okay.
Actually, this that open string like behavior of the
Yeah, only happens in the induced vacuum actually.
Yeah, the open string behavior. But we in order to understand that, we need the oscillator vacuum. Actually,
Yeah, I think this C and C tildes are the oscillator vacuum actually. Yeah.
Find on the oscillator vacuum. So had the equation. I mean, the which state?
Yeah, I know this thing. Yeah. So basically, the C and C tilde are the oscillator vacuum, and C and C tildes are defined like you can act C acting on 0 C equals to 0, and C tilde. Yeah, alpha and alpha tildes are the tensile mode, and these are the oscillator vacuum here.
Okay. Okay.
Yeah, oscillator vacuum satisfy the same algebra as alpha alpha tilde in the tensile theory. Yeah. Yeah.
Okay. Thanks.
Actually, one on the one of the particular study actually, and here
Yeah, I think there are recent. You also worked with.
I don't think we're talking about the same people. My cousin people is reviewing this theory as a new theory. And
Was reading some recent paper. There, people were constructing the vertex operator, and they said that in the fluid vacuum you can do a path integral quantization. Other vacuum, the state operator correspondence is not well defined. I think there are some issues about different kind of vacuums. I think.
So I have a question. I think this is related to this Hagglund transition and back to the
Yes.
it is this article written.
Yeah.
They claim that after you beyond the Hagglund transition, the effective theory is like a two-dimensional theory, and his analysis is just based the calculation of free energy that is proportional to the temperature squared. So they claim like string all those study have there are some connection with this statement.
You were saying the becoming two-dimensional in the Hazard. I am not very much familiar with this actually, but I think here you can view that T is proportional to Hadron temperature and 1 minus some T square by T naught.
Effective tension is, yeah.
And
when we take tensionless limit, actually effectively the Hadron temperature is volume of
Yeah, I know. So I wonder that's why I'm mentioning this Hagglund transition. I said this is related to this tensionless.
Probably they showed that I mean when with thing close string, I mean a gas of string can be heat beyond the Hadron temperature. There is a long string system and something like that, right?
yes,
Actually, we think that similar things happen here actually. But some kind of actually when we try to understand tensionless string, I mean tensile string and take tensile, if we take tensile string state and take tensionless limit,
yeah.
there is a both Einstein-like condensation happen on the.
So Bose-Einstein condensation is the same as the Hadron transition. So basically all the tensile string modes will condense into tensionless string theory mode.
Previously, you said that for these
Yes.
approach, this induced vacuum doesn't have a critical dimension. Dimension can be anything.
Yes.
But you said that there's the other two vacuum has a critical dimension. What are they? What's the dimension of that?
26. The other two are 26.
And 6.
I think the idea here is that the Lorentz algebra, if you construct, then for the induced vacuum, it is you can have any dimension. Other require the 26.
But still, I think that I mean, if we start with a 26-dimensional theory on the tensile counterpart and take tensionless limit,
Then it will be 20 years. The intrinsic tensionless theory, and you want to calculate that what would be the dimension, then you can independently say that induced has no dimensional restriction, but other two has some d equals to 26. t equals to 2 is required, I am not familiar with this literature. Why d equals to 2 is required, you were saying? Yes. Yes. Okay. Saying the pre-rent scaling as t to the power 2 is restricted by the d equals. Yes. Yes, yeah, yes, I think. Okay. Some contradiction. Here we don't require anything here. Yeah.
So comments. If not, let's thank the speaker.